Okay, so now let's turn to the fourth equation of Maxwell. Now, this law was originally given by Ampere. He said that if we consider a loop around a wire which is carrying current I, then the line integral of the magnetic field around that loop will be equal to mu naught times the current that is carried by the wire. But Maxwell noticed that this law cannot hold in a certain situation. The Ampere's law is incomplete. For example, let us consider the following case, where we have a parallel plate capacitor placed on the wire. So now if we take a loop around this point of the wire like this, and then apply Ampere's law, we'll get this equation. We can write this down because the direction of B and DL are perpendicular to each other. And for a constant I, the B on this circular loop is constant as the distances are same. So we can take the constant B out of the integral and integrate this DL over the whole circumference, which gives us this circumference 2 pi r. And according to Ampere's law, this is equal to mu naught I. So we have B equal mu naught I over 2 pi r. Now you have to be a little careful about this current I, which according to the Ampere's law is the amount of current that passes through the surface. But Ampere's law doesn't specify the geometry of this surface. So, in order to find out what's wrong here, let's find out what is going on inside a parallel plate capacitor. Now, the current I is continuously accumulating charge on the parallel plates. So, if at some point the charge on this plate is Q, then the charge on this plate should be minus Q. And as the plates are very close to each other, the electric field here can be considered constant, which we can find out by this equation, where A is the area of the plates and epsilon naught is the permittivity of the medium inside the capacitor. So, although no electric current is passing through the surface, an electric flux is passing through. And we can write down that electric flux to be equal to the electric field E times A, as the electric field E is constant through this area A. Now, by applying Gauss's law, we can write down this electric flux to be equal to Q divided by epsilon naught, where this charge Q is the charge stored on this plate. So, from this equation, we can see that charge Q can be written as epsilon naught times the flux phi E. But we know that this Q is not constant and it varies with time. So if we take a time derivative on both sides of this equation, we get this. And this rate of change of charge is what we call the current, I. So we see here that an electric flux that changes with time is actually equivalent to a current, which is given by this equation. So, to correct the inconsistency shown earlier, Maxwell proposed to add that extra current term in the Ampere's law, and that current is known as displacement current. For a more general case, this electric flux can be written as a surface integral of electric field. Then Maxwell's fourth equation can be written in this form. Now, if we apply this equation in the previous example, in both cases we would get the magnetic field to be equal to this quantity. Because when we will consider this surface, there will be no displacement current, only this current I, and when we will consider this surface, there will be no this type of current I, but the displacement current, which is actually equal to I. So let's check that second case here. So the line integral here is equal to the displacement current term. This thing can be rewritten as Q divided by epsilon naught, which you can see from this simple calculation. And this rate of change of charge gives you the current I, leading to exact same equation as the previous case and the exact same magnetic field. So the summary is, along with the normal current, we have to consider another current which is known as the displacement current due to the electric flux in the fourth Maxwell's equation. Now, for a more general case, the mu naught I term can be rewritten like this, where this is the current I. Here, current I is defined as the surface integral of a quantity which is known as the current density, J.